What's up, guys? I hope you all are doing well. Welcome back to my YouTube channel and welcome back to another YouTube video. In this video, we will be looking at part 4 of our SciPy package exploration, and you guys know it forms part of the tutorial series Scientific and Numeric Computing in Python. So, if you have been following along, right? From the beginning of this tutorial, essentially what we did is we explored the SciPy package. So in the first tutorial, just to give you a sort of refresher, if you remember in the first tutorial, what we did is we understood the package itself, SciPy, Scientific Python. We proceeded further to just get a bit of factual information about the package. Okay, essentially, the most important thing we did in the first lesson was that of exploring the sub-package that is known as constants. Okay, as you guys can see, I have the code here still from the previous videos. So that was the first lesson, the primary, most important concept. Now, in the second lesson or tutorial or lecture, essentially what we looked at is the topic or concept of trying to basically solve optimization and minimization problems using a SciPy package. And if you remember, we were introduced to the curve fit function. So that was interesting. Okay, if you remember correctly, we did look at 3 examples. We looked at a straight line example, a Gaussian distribution, as well as a line spectra. So that was the equation in which we had 2 Gaussian distributions, or the equations. That was the previous video. Basically what we looked at is functions, and we looked at basically solving some answers, or solving a few questions rather, to those distributions. So we learned how to find the roots of an equation, okay, as well as we learned how to, yeah, I think it was mostly that, if we are correct, it was mostly to do with the finding of the roots. And if I am not mistaken, we also looked at the intersection. So as you can see, I have it here. We defined, basically we solved one problem in which we simply try to find the points of intersections of 2 equations. And as you can see, we use the trigonometry distribution as well as a simple straight line graph. So we found those points of intersection. So I will run this just to give you a bit of idea as to what we are looking at. Now, keep in mind that this is for those videos that we did previously. That was just a brief overview. Now, this is part 4, okay? And what we will be talking about now is this concept, is very interesting concept called interpolation. So I will comment that here down for you. Interpolation, okay? Like how you get extrapolation, now we are looking at interpolation. So essentially you may ask, right, or maybe it is you forgot what interpolation is. I mean, what we are talking about all this while is our high school maths, right? And I also just had to give myself a sort of overview about certain topics. So I will just briefly give you an overview of what it entails. Now essentially, you see, to put it simple, in a simple way, interpolation is the, I would say, the technique or procedure of being able to deduce a new data point based off given data points. Okay, it's the way of determining a value using the existing values that we have in the data set. Okay, and by data set I am referring to anything that we are dealing with. So if it's in the form of the array, but in this case, if we have a scatter plot, for example, and we have a few data points that we can plot on that graph, if we are asked to sort of give the value, right, of the y data point at a certain x, what we would do is we would utilize the existing data points on the scatter plot, and we'd sort of just logic it out. Okay, so I hope that makes sense. Now essentially, right, you'll agree with me when I say that data that contains useful information can always most likely be represented in a functional form. Okay, now if you don't understand what I'm saying there, what I mean is data that is given to us will have the ability to have a curve fitted to it, and essentially that curve would give rise to a function, as you saw in the earlier lessons how we utilize the curve fit function, because all we did was just generate random data, and using the curve fit function, SciPy has given us the ability to now obtain a functional representation, right, in the form of an equation basically for that distribution. Now, you see, if functions have the ability to be, or rather, if data points have the ability to be represented in a functional form, right? Now, the thing is, we as data analysts, okay, data engineers, we want to model it. That's the whole point. The whole point of SciPy is to help us with modeling and fitting of data. Those are the two broad, I would say, categories of what we are doing. Everything we are doing falls inside those categories, okay, modeling and fitting. Now, you see, essentially now SciPy as a package, it offers, a variety of different functions that we can use for interpolation. Okay, it will cater for those situations where we work with maybe univariate problems or multivariate problems. So to give you another bit of insight, univariate interpolation, so I will type the spelling of that down for you. Univariate interpolation. Now, univariate interpolation is basically used when the sample data that we are working with is likely to be led by just one independent variable. Okay, so univariate interpolation, one independent variable, and as you guessed it, multivariate interpolation, multiple independent variables. So essentially what multivariate interpolation is when we have two or more. So let's type that down as well, right? Two or more. Now, that is fine. Now there are two basic methods in for us to do interpolation, right? We'll have the ability to fit one function to the entire data set, or the second way is we can fit different parts of the data set with different functions, appropriate functions that match that kind of curve. Now, essentially, if we are doing type 2, where we are fitting the different parts of the data set with a different function, what we'd have to do is we see where the joints of the function, essentially where the joins of the function are, basically the ending points of each function, we'd have to find a way to smoothly join them. Okay, now the second type, right, the type in which we utilize several functions to actually fit a distribution, that's known as spline interpolation. So spline interpolation, spline interpolation. Just to give you a recap, type 2 of interpolation, the type in which different parts of the data set are fitted with different functions and where the joints of each function are joined smoothly, is known as spline interpolation. Now, spline interpolation, as you guessed, it is the more complex type of interpolation, and it is much more powerful, especially if the data that you are working with is, I would say, kind of multi-dimensional or complex in nature. Now, what I'd like to do, guys, for this video, I'd like to demonstrate a simple example of interpolation, and maybe we can take it one step further to a kind of difficult example of interpolation. Now, what you will see is, for this first example, we will utilize the sinusoidal function. Okay, so I will type that down for you. A sinusoidal function. Now, don't get intimidated by this kind of word. Okay, essentially what it is, anytime you hear the word sinusoidal, it's basically referring to something that is based off the standard sine function. You know the trigonometry sine? So sinusoidal function is a function that's based off of this function, the sine wave. So that's fine. Now let's proceed. So what I'd like to actually, mention to you is, for this example, we are utilizing the SciPy.interpolate subpackage. So I will just do my importations, then I will explain to you guys. So go ahead, type from SciPy.interpolate import interp1d, right? Interpolate 1d. So essentially we are using the interpolate subpackage from SciPy, and from within that interpolate subpackage we are grabbing or wanting to use the interp1d. So I will bring up the documentation for this function on the screen just for you to have a look at. So I just want to talk about three parameters for now: x, y, and kind. So these are kind of self-explanatory parameters. So as you will see, right, x and y are arrays of values used to approximate some function. That's fine, that's nothing difficult. And kind here is the important one. It's the kind of interpolation that we'd like to kind of proceed to do, right? Is it linear? Well, for now, the two that I want to focus on is just linear and quadratic. So in the first example, you will see we are working with a linear interpolation. So that's that. Now, that's all you need to know for now about the method itself. Okay, everything else is done by the method, and I will not be going in depth into the math behind the method because I assume you know what interpolation is, or you have some basic idea of how the process works. Okay, essentially it allows us to be more accurate when guessing our values. Think of interpolation, really guys, all think about it as smoothing the gradient of the function. That's what you need to think of it as. So let's proceed further with our example. Now what you will realize as we do more of these SciPy examples is that the way in which we proceed to tackle a question, well, for now, is very similar. So what I mean is we import, we generate our sample data, we proceed the operation, proceed to do the operation that we need to, and then we will visualize it. Okay, the visualization portion has been added by me in this tutorial because I want to make sure you guys have a good understanding of what we are working with. So let's do x is equals to, I forgot to do numpy, so np dot linspace, and we'll do 0, 10 multiplied by numpy dot pi, and let's say I want 20 values. So to do y, let's probably just make it a cos, so numpy dot cos of x, and that will give us the appropriate answers. So we have the pairs of data points, the x and the y. Okay, now what we want to do is interpolate the data, but before we do that, head over to the top of your imports, import matplotlib.pyplot as plt. Now I want to just visualize the existing data points we have. So plt.scatter x and y, plt.show. So we can do a scatter plot first, and then I would like to do a line graph. So as you can see, the points look like that. So let's do plt.plot. So as you guys can see, this is the graph. Let's work with the line graph. So we'll be utilizing plt.plot. You saw what the scatter plot looks like. When you join those dots, this is what you get. Now let us proceed to actually play around with the interpolation function. So first things first, what I'd like to do is head over here, and I will comment the plots out for now. Now we will create the interpolation variables just to store the interpolated data. So essentially what I can do is I will just say maybe uh, interpolated, we'll just call it f. Okay, so, or maybe we can just call the graph itself f, and since we are doing the linear kind, we'll just call it L, and we'll say inter p1d, and we are passing now the data that we'd like to interpolate. So let's do x, let's do y, and suppose we just like to leave kind is equals to linear. It's the default arguments. Okay, now let's proceed to do that. Now if we view fl itself, so it is the interpolation object. Now fl is the object, the interpolated object. Fl is the kind of new, I would say, equation in inverted commas. Now it has x and it has y values. So you actually can go ahead and view this, right? It's actual values that reside in there, appropriate x and y values. Now if you would like to have a visualization, we can. So let's proceed to do that. plt dot plot. We are working with the line graph, x and y. Oh, I actually had it here. I could have just uncommented it. So you guys saw what this graph looks like. It's the one we just ran, right? Now let's view the interpolated data. So fl.x, fl.y. And as you guys can see, there is no difference, okay, between the original and the interpolated data. Now let's proceed. Just as a test, we can use the quadratic interpolation. So inter p1d xy kind is equals to quadratic. You guys can go ahead and play around with the other types, right? I specifically just want to demonstrate to you linear and quadratic, so that's fine. Now it's the exact same thing, but instead of visualizing FL, let's visualize FQ. So I hit Control Enter, and as you guys can see, I have a graph and it is exactly the same. Now there has not been much changes. Now you may ask yourself why? Why am I not experiencing any change, in the graph's visualization? It seems like the inter p1d function did not really do anything for me. Now, the answer to that question, guys, is actually we are getting to that point. What we are visualizing is the raw, I would say, graph to what, or the raw data to what we are interpolating. Interpolation is a kind of interesting process in math, and the key aspect of interpolation, as you guys will see what we will perform now, is basically the restricting of the domain, the x values, when we are interpolating. You may be wondering, right, that the data we have is exactly the same before and after the interpolation process. But now I'd like to mention to you, right, do you remember in the beginning when I told you that the two main categories we are working with is data modeling and data fitting? Now you see, essentially, right, what has happened in the first process here, what we have done here is the fitting of the data. Okay, we have given the interpolation function some idea into the data. Therefore, the values that we have been plotting, the FL and FQ, X and Y values, we are not noticing a change because those are the original values, right? Now, essentially, what we have achieved in this step here, so I will add a few comments, right? What we have achieved here is obviously interpolating the data. Now, we have created a model. So I will say a data model. The model has been created. Now it's time to use that model to attempt interpolating or getting the values, that we need. So essentially, just to give you a bit of insight, right? I have sourced this statement from Medium and I found it super useful. So as you guys will see, so interpolation means applying the model to predict the value of a dependent variable on independent values that lie within the range of the data we have for analysis. Extrapolation means predicting the dependent variable on the independent values that lie outside the range of the data. So I hope that just gives you much more insight and explanation into the concept of interpolation and extrapolation. Extrapolation was a common procedure that we performed in high school math. Okay, not so much interpolation, but now we are working with interpolation. So what we have is a model. Now it's time to use that model to interpolate the data. Now for that, as you guys will see what we do. So I will add a few comments here. Import the necessary packages. Here what we are doing is generating the fake data, and here we are visualizing the data points. Okay, so let's move further into the discussion. Now, the next important step that you will apply to your interpolation process in Python syntax is I'm adding a comment here, guys. X.min and X.max are used to make sure that we do not go beyond the boundaries of the data for the interpolation. Now the reason why I'm adding this comment is because this next step is based off of this statement. This statement gives us the logic, okay, the one in the doc string. Now it gives us the appropriate logic and the basically the reason as to why we are performing this step here. Xmin and Xmax, and if you remember Xmin and Xmax, X, what is X? X is the data itself, the data points itself that we were working with. In this case, we generated the data ourselves. Now, those points are used to make sure that we don't go beyond the boundaries of the data for the interpolation. Now, essentially, Xmin and Xmax is going to cover the entire surface area of our distribution, right? Because the minimum X value is 0 and the maximum is 31, which is basically the end. So I hope that makes sense to you, right? It's important to pay attention to the data we are working with. Now, what we will do is X interpolated is equals to numpy.linspace. Now we are generating the data points within which the interpolation can occur. So x.min, x.max, min and max are built in Python functions, or rather methods that can be used on the numpy array. Now suppose we'd like 1000 points, and now what we do is y interpolated in the linear form. And if you guys remember, y is basically the y-axis, the y value. So y interpolated in the linear form will be basically equals to fl, and as you guys remember, it's the model we created earlier, fl model, and within this we can pass the value, so xint. And now before we proceed to view the quadratic form, I'd like to visualize the stuff first. So let's do plt. So I will create a new cell here, plt.plot. Let's do x and y. That's the standard one. We've been viewing that for some time now. And now let's do x. Oh, so if you guys actually forgot to comment about that, so as you guys can see, we have this y int l. It's that array which is containing the numbers or the y values for the x int array, which is basically the x values. Okay, now as you guys will see, That is the linear. Now I would like to do the quadratic. So for the quadratic, it's nothing difficult. What we will do is y int q. So we can call this now fq, and within this x int. Now I want you guys to see the difference, right? The linear is not making any difference on this interpolated distribution. Now let's try the quadratic just to see. So what we have there is plt plot x int y int l. Now I will change this to plt dot plot xy x int y int q and plt dot show. And as you guys can see, essentially what has happened is we now see two gradients on this distribution or on this canvas, and the blue is the original. Okay, as you can see, what's happened here is that the gradient of the distribution or the function itself has been smoothed. Okay, and now logically speaking, guys, all I want you to do is think of interpolation as smoothing the graph. And now as you can see, right, the interpolated distribution, or the gradient rather, is representing that of the sinusoidal function, which is why I said a sinusoidal function is any function that's based off the sine function. Okay, it's in the form or takes on the shape of a sine wave. So as you guys can see, we have interpolated this graph. Okay, we have the ability to deduce or logically provide reasoning for the value of a data point that is just based off the existing point. So essentially, by interpolating this distribution, we have a set boundary 0 to 31 point something. You guys saw that earlier, and we now have the ability to, with some accuracy, I would say, we'll be able to tell the value of any data point that is required. So I hope that you guys find this interesting. Okay, now this was just one example that I showed you, right? There is more that we can do. So now what I'd like to do, as just for extra information, additional information, is show you another type of interpolation, and it's basically the univariate spline. Okay, so spline, we spoke about that earlier. Now let's proceed to do that. So import numpy as np, import matplotlib.pyplot as plt. There is no need for me to re-import, but I'm doing it just for the sake of this cell. We have created a new cell, so let's have the script looking neat. So from SciPy.interpolate, and I also need to upload the code to the previous exercises and tasks that we worked with on my channel. So, or I'll do that to my website rather. So import univariate spline. Now exact same process, let's generate our sample data that is fake. So importing the necessary packages, generating the sample or the fake data. We'll do numpy.linspace start stop. Let's do 10 multiplied by numpy.py, and let's do maybe 30. So that's fine. Now suppose that we'd like y, and y now is going to be the y value. So for the equation we'll use, let's use another sinusoidal function. We'll do numpy.cos of x plus numpy.log. Let's do log 10 of x, and let's do plus numpy.random.randn sample over 30. Okay, so that is fine, or rather I should do 30 over 10. Now that is the equation. You guys can use any equation you want, right? Oftentimes students tend to get confused, especially if it's in a book or an online YouTube video, when the teacher is kind of using a function, the students can tend to get more intimidated by the function itself rather than paying attention to the technique that is used to perform the operation. Okay, so logically speaking, I could have used a straight line graph here, a simple y is equals to mx plus c, but this is just a function that I sourced from documentation itself, and you guys can play around with any function you want. Okay, so essentially think of it such way: using this type of function fits the procedure or the nature of operation that we are trying to perform. Okay, we are trying to perform the univariate spline operation. So let's proceed now to interpolate the data. So what I will do is just call this f, let's do is equals to univariate spline, and within this we will pass x and y, and s is another parameter we need to pass, but s most oftentimes you will set it equals to 1. Remember to do that, guys. To keep it simple, you guys really need to think of S as the condition that basically governs the smoothing. Okay, essentially what you can think of is, you see guys, by default S is none. Okay, so as you guys can see, S is defaulted to none. Now essentially S is, as you guys can see, the documentation says S specifies the number of knots by specifying a smoothing condition. Now, to someone who is just learning SciPy as additional knowledge, especially, I mean, you may not know exactly what this means, but logically speaking, all you can think of is, you guys remember, right? I said that we are working with data models. We can use those data models to make predictions. We can predict the value, of an unknown observation, of an unknown value. Okay, we can obtain its value. Now, think of S as the factor that governs the accuracy of that model. Okay, what's typically said is that the lower the value of S, the higher the accuracy, but that's not always the case. S can be set to 0, 1, or none. Okay, the choice is yours. Now let's set S equals to 1, and what we will proceed to do is the exact same operation as before, restricting the distribution, the domain, to the minimum and maximum, or within the min and max values. So I will not comment that. We had commented that in the previous example. So x int is equals to numpy.linspace. So let's do x.min, x.max, and suppose again I'd like 1000 values within that min and max values. So now what I can do is y int is equals to f. This is me using the model x int. So one thing that we actually didn't do is we didn't visualize what the x and the y data looks like. So let's proceed to do that now. plt.plot x and y. This is our raw data, our clean data. So I hit Control Enter. As you guys can see, this is the graph we have. Now, essentially, logically speaking, before we even work with this example, what we are expecting is to see this distribution smoothed out by the process of interpolation. Interpolation smooths out those rough edges or points in the distribution. So let's view the interpolated value. So plt.plot, and now we'd like to obtain x int, y int. I can go ahead and run this. I actually made a mistake in my variable name. Y int, x int, y int. That's good. And as you guys can see, this is exactly what we were expecting. That's what interpolation is all about. It's all about smoothing the values, bringing them to a kind of standardized form. Okay, so I do hope you guys understand, you are finding this interesting, because it is good to just explore different topics and areas of a programming language. So option S, as we spoke about, it's the smoothing factor that can be used, right, when we are finding data, or sorry, when we are fitting data. Now, essentially, we have the ability to change S to 0. Let's do that. Let's see what effect or change it brings in the process. As you guys can see, right, there is not much change, but logically speaking, when S was changed to the lower number, which was 0, as you can see, the accuracy is, I would say, improved because of the fact that the interpolated gradient lies very close to that of the original distribution's data points. So as you can see, you guys can go ahead and play around with that. It is all interesting stuff. Now, this concludes part 4 of our SciPy tutorial series. Now, in the next video, we will continue exploring more concepts. I would say the next concepts we will explore are relatively easier. They are nothing too difficult to understand. It's basically just a bit of statistics that we will be introduced to. So with that, we will end this video here. Thanks for watching, guys. Thanks for staying till the end of the video. Good luck with your work, and I will see you in the next YouTube video.